In this video, we explore the critical role of torsion rotations in shaping the conformational space of small organic molecules and how you can analyze them in MolSoft ICM-Pro. Understanding torsion profiles is key to many aspects of computer-aided drug design, especially when evaluating whether a modeled ligand conformation is realistic or overly strained. When designing or modifying potential drug candidates, one of the most important questions is whether the molecule can naturally adopt the proposed conformation that you have. For example, could a chemical modification relieve the strain, or could a modification introduce new torsional stress? I will show you how you can interactively rotate torsions and visualize the statistical torsion profiles. I will show you how to calculate the statistical torsion profiles, and also how to estimate torsion-free strain. In this paper by MolSoft scientists Eugene Rausch, Ruben Abagan, and Max Tocherov, they describe a graph convolutional neural network method, GCNN, for learning and predicting statistical torsional profiles, STPs. The approach involves training a specialized GCNN torsion profile model on structures from the crystallography open database. The GCNN STP model effectively captures torsional preferences across a wide range of torsion rotors and accurately accounts for the influence of nearby atoms and functional groups. What's more, the statistical profiles predicted by GCNN STP show strong agreement with torsion energy profiles derived from quantum chemical calculations such as those based on density functional theory, DFT. We'll demonstrate how these GCNN STP profiles can be applied to improve conformer generation in structure-based drug design. In this example, I'm going to read in a milk protein with a milk inhibitor. It has PDB code 4BKY. This is an X-ray structure, so anything to do with torsions, we need to first convert to an ICM object. You can do that by right-clicking, convert PDB, use these options. There's other videos that describe ICM conversion, and just go OK. Once it's converted, you'll see that it says X-ray ICM here. It no longer says XR for X-ray, so it's an ICM object. That means we can start looking at the torsions of the ligand. So if we just display the ligand, zoom in, go to the display tab here, check on the variable button, single click, and then you see these green rings. So a thin green ring means that the torsion angle is close to its minima, which is preferable. A thicker sort of yellow to red ring, like this one, for example, shows that there may be some strain at that point, that it's not quite at its, the angle is not perfect in terms of the minima. So we may want to rotate the torsions and see the effect. So if we click on this button here, it will be shaded dark if it's selected. Then we can select a torsion, and then you can rotate. So you can see as we rotate, this is probably a more preferred angle for this torsion. See, this ring has turned into a thinner green ring. And you can also see in the top left-hand corner the torsion profile. So as I move around, you can see the red box going up and down the torsion profile. As we get away from the minima, that ring turns reddy orange to red, like that. So probably this is a better angle for this torsion. You can do that for any other torsion. You just select it and then rotate like this. So what if you've generated a set of conformers and you want to look at the torsion angle and the profile for each of those? I'm just going to do that for this ligand. So I'm going to extract the ligand as a 2D drawing. And you can see it's a right click on the ligand and it extracts it to a chemical spreadsheet. Then we can go to chemistry, generate 3D conformers. This opens this dialog box, and you see at the top here we have some different tabs. Ginger is the fastest conformer generator on the market at the moment. Uses GPUs. I'm not going to convert this single one using the GPU. I'm going to use it using CPU, using this tab here. These compressed databases are used for our ultra-large library screening, which use pre-generated conformers. You can also do it directly from a file if you wanted to, but I'm doing it from a loaded ICM table called chem. So a number of different options you can choose. I'm going to choose the neural network assisted sampling using the method described in the paper that I showed earlier. You can, if you have many to convert, you can parallelize the jobs here using multiple CPUs. There's a number of different options and Monte Carlo options you can change, which I'll put the link to the manual in the description. But we can go OK, and then this will generate the conformers. It's finished. Go OK. So now we have a table called conformers, and we have 8 conformers for this ligand. I'm just going to undisplay this one. So they're ranked by energy. This is the most energetically favorable one. You can see that there's rotation here. The second one, third one, you can just toggle them on and off here. But what if we wanted to look at that torsion that we were looking at earlier, which seemed a little bit strained in the X-ray structure? We can calculate the torsion angle for this region for each of these conformers by going to the chemistry menu, choose torsion analysis, and it's asking you which table you want to analyze. We're going to analyze the table called conformers. The mole column contains the chemical. And we have a torsion pattern. So you can use smart string to define the torsion. So I'll just show you. I have this already made. So we can use this. You can enter it smart, or you can sketch it by clicking here. But the key thing is, so this matches this group that goes to the ring here, on here. So the key thing is to define each of the atoms using atom mapping number. So you have 4 for the torsion. You'd have 4. So you right click 1, atom mapping number 2, 3, and 4. Okay, close, and then you can choose. You may have multiple matches, and you can of the smarts. You can try all of them. And we're going to build the angle distribution histogram here. Go OK. So now we have the angle, the torsion angle for each of the conformers that we generated. We have this plot, and we know from when we rotated the crystal structure ligand that probably a good torsion angle for this torsion is probably around 60 to 100, around that region there, 120. So if we had, we could maybe, you can select those that are in that range here, or you can select the ones that are outside the range and just maybe delete those, and you can see this is the torsion profile for that particular torsion. You may want to calculate the free strain, which is the strain of the torsion of the chemical based on its statistical profile plus an entropy component. So to do that, you can go to chemistry, choose calculate torsion free strain, give the chemical table. You can parallelize this if you wanted to, but we've got a very small table, so I'll just go OK. And then you get the free strain here. So the lower this value, the better the free strain is. So those are the main key features of the torsion analysis tools in ICM. They're also available in the ligand editor. I'll try and put a link to that in the video as well. So you can, when you're editing a ligand, you can also monitor the torsion angles and then the profiles as well while you do it. Thank you.